Yeah, thank you very much for the invitation. My name is Dirk Tiede. I'm an associate professor at the Department of Geoinformatics at the University of Salzburg. I did that work not alone, so my colleagues are also written here on the slides. We are very happy that we received, I think, one of the first OCRE grants for Earth observation research. And that helps us a lot in making our research happen also in the era of big data. I want to present a bit what we are doing. I also want to present a bit what is the topic we are dealing with. I hope it's interesting for you. I'm not so much aware what all your backgrounds are, but I tried to keep it condensed form, and I'm then open for any question also regarding the cloud services we are using and so on. The title of our approach is the Sentinel-2 Semantic Data and Information Cube for Austria. We developed that in Austria, but in principle, it's scalable worldwide. So that is one of the core components in here. What is the motivation we have? So I'm dealing with remote sensing, with images. That is Salzburg, visited from Sentinel-2, one of our nice European optical satellites. We get here images every 2 to 5 days, depends on overlapping orbits. These images we have worldwide since a few years, not only from this program, also from other satellites, can be radar satellites, can be Courser satellites, and so on. The Copernicus program of the European Union is the third largest data provider worldwide. So they claim they are the third largest data provider, maybe they are the fifth largest, and so on. The source is not perfectly secured here, but it's one of the biggest data providers overall and the biggest Earth observation data provider. We all pay with our taxes these Sentinels, and all the data is freely available for everyone. That's a really big change in how the satellite data is distributed. And we have at the moment alone from that program 34 terabytes of data available, which can be used for free for everyone if you are able to deal with that big amount of data. There are different satellites. I will not go into detail. We are concentrating on optical images, which we can see as humans, similar with our with our mobile phones. There are other types there, but that's not our topic today. We have here an unprecedented volume, variety and velocity of Earth observation data in the last years that started a lot with a decision of the from the US to opening their archives in 2000, I think 8 or 9 for the Landsat satellites. The first time that all the archives were made freely available. When I studied geography 20 years ago, it was maybe possible to buy one scene and then you did 3 master theses out of that single scene. Nowadays, millions of images are available free, and the European Union also decided to make their data free, and you see that on the very reddish green colored bar here, how that increased in the last years. And on the right side, you see also how the users who use the data are increasing here at the European Space Agency access point. And the big thing is in here that we change from bring users to the data, not the data to the users anymore. Also in our domain, US cloud managers, you know that from any other domain maybe as well, but in the Earth observation domain, that is new because the data is now really for everyone available. That is that satellite. There are actually 2 satellites in sun-synchronous orbits called Sentinel-2. They are making images like you see in the lower right. That's 1 year Vienna. Some of the fully cloud covered things are filtered out, but you see you have every 2 to 3 days a new image. Each image has 10-meter resolution, 10,000 by 10,000 pixels, and is roughly 800 megabyte in size, and has different spectral bands, also in electromagnetic radiation we cannot see with our eyes, so near infrared and so on. And on the larger figure, you see how the whole globe, at least the land area, is covered by that. And we have since 2015 these satellites in orbit and have an enormous resource we can analyze, especially for global monitoring of any kind, whatever. climate change, emergencies, forest change, agricultural issues, soil sealing, and so on and so forth. So it's more generic. It's not tasks for any city. It's always recorded all the time for any place on our globe. That causes some changes in workflows. We see that here from publication we did a few years ago. On the left, that was what I explained before, how we worked usually 10 years before. And yeah, some of us are still working like that. So you download data, maybe one scene, maybe 10, you do your pre-processing, you do a map production, and you deliver that to the end user. But with this enormous amount of data, that is not possible anymore. So the data pre-processing and also an analysis switched to the cloud. We cannot handle that anymore. And at the moment, the analyst is doing the work in the cloud, and also the results are usually online resolutions, online results, streams, whatever the user needs. The big problem is now for us as a small research group that the big EO data analysis platforms, which give access to all of the data, are now occupied, I would say. I mean, it's also nice that they do that, but we have the big players in here now. So Google Earth Engine is the most prominent one in here. They are offering access to all of that data for free. They're offering an online processing environment. Microsoft Planetary Computer, also Microsoft is going into that direction. Amazon is making also the same data publicly available with their nice S3 storage and stuff like that. So these large companies and other big providers offering that and offering scientists to work online in their pre-configured platforms. No need to consider difficult data structures, software and hardware requirements. That is nice. A lot of publications come out of that. A lot of scientists worldwide are now enabled to do that online cloud analysis of these data sets. But there is a but, that's why I'm here. The dependencies on such specific platforms, the data and the functionalities give you less of control that may limit the diversity of users. It's limiting the research and development parts, especially in the back end where the data is handled. So it's all predefined from these big providers. And so we argue, and you see the article, a screenshot of that we published last year. Think global, cube local. I will explain what we mean by cube. These are the data cubes we are using. So we are arguing that it should still be possible also for smaller research units, for other countries, also in the global south and so on, that big data analysis in the Earth observation domain should not only be solved by these big companies. It's nice that they are offering that, but there should be room, and not only for the big players, to implement their own algorithms, also in data handling and data pre-processing. We have developed an approach for that, and we are quite proud of that. We created a different approach than the big providers have in there. We want to make also fast and easy accessible Earth observation data in cloud-based analysis workflows, but we want to provide that in a programming-free environment. We want to enable users to make their own queries on data with a new approach we call semantic Earth observation data cubes. I will explain shortly what that is, if that is not so much of interest. I will skip that a bit, but a few things I want to mention here. What we need for that is access to computing, facilities, storage, and big EO data resources in the cloud. There is OCRE helping us a lot with that grant. So we not have only access to the pre-processed data, we have access to the data and can pre-process in the cloud as well. And we create our own cloud services for other users based on that with our new approach, which is different to the ones the big providers are providing. And since we are a small team, four employees plus students, PhD students and master students, we need these additional infrastructure support we got in here. That is our idea. It's published. It's the first semantic geodata cube proposed to date, and that's why we are quite happy with that idea. What is the core idea? We have 3 elements here. We are, in contrast to any other provider, pre-process all of the images by semantically enriching every image to a categorical variable. That means we interpret each pixel which you can photograph by a label. This is strong vegetation. This is bare soil. This is water. This is turbid water. This is cloud. This is shadow. This is snow, and so on. And with that categories, we fill our data cube together with the images. You see that here. The second part is the data cube technology we use. For that, we need big storage, fast computation facilities. The data cube approach gives us the opportunity to access the data not based on flat files, but on area of interest. The data cube indexing the files based on the geographic location. And if I define an area of interest, not all the files will be taken into memory, only the area of interest will be taken out of that data cube approach. And the third approach is what we developed as our cloud service. It's a web-based inference engine. So everyone, you, authorities, experts, can do then in a browser, mobile phone, a semantic querying. That means a spatial querying through time, for example, looking for forest changes in a storm-damaged area, or looking for changes in the water level of lakes last summer, or looking for snow cover, and so on and so forth. It's generic. We are offering a new analysis platform for Earth observation experts. The semantic enrichment, just again here an illustration, gives us like a semantic skin over our data sets. That is fully automated. We have an approach there which is called satellite image automated mapper. We are scaling that up, parallelize that in the cloud. So the provided cloud services help us in making that faster and faster. Here on the slide I have written it's approximately 5 minutes per scene, so per image. I have just heard from my colleagues, we are now on 2 minutes per scene with the parallelization we did in the last weeks. That looks like this. You see here Salzburg in the lower part. That's the Salzach River, in-river, and that is the semantic enrichment automatically for each scene, and that we use in our cube to make that available. The data cube technology, as mentioned, gives us a view on the data without looking into the flat files anymore. We are indexing the files based on the geographic location. And then if we make such an AOI, we can query only that part of the images through all the images through time. It can be hundreds of images, and we only access that part, makes it much more faster to process. And the semantic data cube approach on top not uses only the value we see in the image, the reflectance value, which we can interpret as a human very easily, but not the computer. So we enrich that by a labeling, which gives us more opportunity to query the data. I will bring some examples later on. And that is now our interface, our cloud service developed on top of the cloud services we use, supported also by that OCRE grant. So that is an inference engine, a web interface where everyone can log in. We have user management in here, multi-user support. We are monitoring that with Grafana in the background. So we try to scale that up in a small, so we try to show that it's scalable, but we are still in a small environment. So we did that now for Austria. We have also, and I will show that later on, also some other areas where we show that it's transferable. The web interface is generic. We can plug that in with different data cubes in the background. So Austria, here is Syria mentioned. I will show that later. We have also one for the Alpine area and Afghanistan that can be extended as needed. And we developed a semantic query language for that. That's a Python library you see here on GitHub, where we created a query language to do the semantic analysis through time with such web interface. These are the queries I mentioned. It's programming free, so that Python query language is in the background. These blocks here, implemented in a software called Blockly, can help you with drag and drop to formulate queries without need to know any Python code or something like that. In the background, that is translated into a query through our DataCube data sets we have in the background. Also for that, I'll show you an example. And the queries select from the DataCube the requested entities like water, forest, whatever you want to monitor in here. That is now the implementation for Austria. That's our proof of concept that it works. All the things is Dockerized. It's worldwide applicable in theory. We show that we can transfer that to other areas, and that our main goal is we show that it works here, we show that it works there. And if we are involved in larger research projects, we can also upscale that. That's our main interest here, that everything can be scaled on the long run. What you see down here is, that is maybe for you not a big figure. We are now, I think, almost 25 terabytes we have in the DataCube. That's for you not much. For us, it's a lot. If I look 5 years back, I could not imagine that we can handle that with just web interface query. The images are growing from day to day because we have always new recordings. That is the architecture, maybe of more interest for you. Everything is scalable, container-based. We are using Docker Compose for the services, horizontal scaling. So we have concurrent multi-user access. So here on the right, you see the EO image archive, and I will come to that later. We selected with the OCRE and the cloud provider, the EODC in Vienna, which has a focus on Earth observation. So they are not only providing the cloud space as such, the virtual machines, the storage, they have all the remote sensing data already there in their storage. So we can pre-process everything there in the cloud. That is done here. We obtain the images, we pre-process them, semantically enrich them. We fill that in our Austrian DataCube. Or if we go to another area on the globe, we have a different DataCube here, different region, different country. That is linked to our knowledge base. That's basically a big PostGIS database where all the queries of different users are saved and can be exchanged. I will come to that. And here in the middle, we have the inference engine where the queries are brought together with different fact bases. And in the graphical user interface, the users, expert or other users can use either already developed models and to repeat them. I will show you different interfaces later, or they can create their own models, which is saved in our knowledge base and can be inferred to any place, anytime in the area of interest. So we use established cloud services to create a new cloud service for big data analysis on the fly, using our own algorithms in the background and not relying on predefined workflows from the big providers. Some examples here, but I go fast over that. That model on the right is a very simple one, defining what we see as vegetation, for example, here in Austria. And we can then run that query over whole of Austria. In that case, we tile that. We're using some Apache Airflow methods to tile that to our cloud resources are still limited. So to have there a tiling of the scene, and then after a few hours, we get such an analysis for whole of Austria that is analyzing thousands of images through time when vegetation was observed. So how green is Austria? How green is Vienna here? We can make analysis based on such a query on large areas. Or we look into historical developments, for example, construction sites, looking into different developments on parcel level. We get these curves out of our interface. We can just tweak that to get these statistic on polygon level instead of getting a map out of that. all the results can be directly used in GIS software, Geographic Information System software, can be also streamed as web map services if needed. Or here an analysis for soil sealing. That's a bit hard to interpret. That is basically an analysis on 3 years of data sets. So that means in that case, around 350 images through time, and then shown as a false color composite. Keep that short. Everything which is very reddish, yellowish, or bluish has a lot of change, and the brighter elements are stable through time. By that, we can very fast indicate how here in Salzburg, for example, construction sites were done, or when different things are sealed or something like that. We have some interfaces created for that. We have now our own service based on that, so we can access that through a browser. We can access that through a mobile app that is at the moment in development. That is the first screenshot. We can directly integrate that in a GIS software, Geographic Information Software, in the workflows of users, also authorities. And we have also things like command line interface for batching and stuff like that. We teamed also up with a company from Vienna, Spotteron. They have a software together with the Met Office of Austria, where people can notice differences in the nature. And with our service, we can bring in here also live queries from these satellite data. That's more or less the last thing I want to show you. Then I really focus on the OCRE provision. That is a demo that's recorded. Let me just have a look if I can start that. I have to change the pointer. So now it's working. So that's the interface. That's live recorded from my screen. You have the knowledge base, the fact base in the inference. So everyone can access that. If you have a user account, you are invited, if you are interested in that, to do that on your own. But maybe you're not the real target group for that, but the offer is there. So here you can do per drag and drop, you can create such queries. That's now a bigger one, looking for vegetation versus bare soil. Such a query can be used to look for agricultural activity, for example, when a harvest took place. You can just drag and drop these elements, you can exchange them, you can modify them. All the models are saved in the knowledge base, can be exchanged between users. So if an expert created a model, a non-expert can still use it and just has to use here the fact base to change where to apply the model. So for example, here an area of interest is drawn, and then a time frame is specified here in the temporal subsetting for which time frame that analysis should be done. And that is all real time what you see here. So we can, with that approach, make all the data available and allow people without programming to run such an inference. We'll just see the result. The colors are not so nice, but have always in mind that can be downloaded and made a bit nicer. And the new version also allows here some more things. You see here now just vegetation versus bare soil through a time frame of a few months. Huh? The nice thing is now that interface is generic. We can, you see that in the lower row here, we have different data cubes. So northwestern Syria, we are using for master thesis. So we analyze here the impact of the Syrian crisis and the war on irrigated agriculture. And that data cube is now not located as at the EODC resources, but at the university, yeah, here in Salzburg. So the interface is generic, and just by switching the data cubes, we could also switch the cloud providers. For example, if there are other data available and so on, we can just switch in here, and that is extendable. So if we are managing research projects, we can do that for other areas of interest. Here you see the same model, the same query, not modified, but applied in Syria. Okay, so let's come to the last slide, how the OCRE project supported us. I mentioned that several times now in the presentation, but now in a condensed form. We got access to EODC resources. We were before already at EODC, and through OCRE, that was a bit a way to go, because EODC was at the beginning not their registered cloud provider, but for the EO grant, the OCRE project opened that, and we could argue why the EODC is, in our case, a very well-suited partner, because they have all the Earth observation data already in their archives. So several petabytes we can just access and pre-process on the fly. That worked quite well. We are very happy. We can now secure for 3 years at least these resources, use them in research projects, helping master students to do their thesis in here, PhD students, also in projects to show authorities, planning authorities, environmental agencies, how they can use that environment. That grant enables us for a really small research group. So we are, as mentioned, 4 people plus maybe 3 to 5 students, to enable us to play in the higher league, not to rely only on Google Earth Engine, on Microsoft, but to really establish, show that our concepts are also working, that we have parallel developments, different ones, and publish about them. And we see from that new established concept that new research questions are emerging out of that. How can that be used? How can that be automized? How can we bring that into larger areas? And last but not least, we can upscale with these resources our proof of concept. Beyond Austria, we have seen already other data cubes, and we are quite happy to be able to do that. The OCRE success story you can get from that link, where we have, there is again a condensed written statement about what we did in here. Okay, thank you very much. I hope it was a bit interesting, not too boring with the Earth observation stuff, and I'm happy to answer any questions you may have.